talk about the working process about introducing an effect system to Scala. This is a joint work with Nicola, Sanjo, Nada, and Martin. We are still at a very early stage of the project, but we do have some initial results as well as some open questions I'd like to share in this talk. So every project needs a justification. Who needs effect systems? Why we introduce an effect system to Scala? The reality is that most Scala programs, they don't care about effect systems. Some programs, they do care. For example, in distributed parallel programming, they care about the functions they send over the wire are devoid of some effects. Also, compiler hackers, they care about that when they do program optimization, they want to make sure their functions are pure. For example, if they do fusion of higher order functions or dead code elimination. The reality has an implication on the goal we want to achieve. So for an effect system to succeed in Scala, it has to incur zero overhead for programs if they don't care about effects, and it should have very low overhead for usage, and also it should have a very low cost for migration of legacy code. As a disclaimer, we're still very far from this goal. So this is a long-term objective we want to achieve in the long run. When we set out to introduce an effect system to Scala, one of the main difficulties we face is deal with the problem of effect polymorphism. So this problem can be illustrated by the function map. Here, what's the effects of map? It's obvious that it depends on the function f, but how we tell the type system this fact? This problem turns out to be very important because in functional programming there are higher order functions everywhere, and most of them turns out to be effect polymorphic. In a classic type and effect system, the way to do it is to introduce an effect parameter E, and then to annotate the effect of F and the effect of map with E. When there are several higher order functions, then the syntax gets heavy. Another reason we don't take this approach is because the migration cost will be high. It means we have to change every higher order function in the standard library as well as the third-party libraries. Another popular approach to achieve effect polymorphism is to use monads. So the way to do it in Haskell is to use a generic monad and then specialize it to identity monad for pure functions, and specialize it to I/O monad for I/O effects. However, as noticed by Nipomer, this approach is rarely taken in practice. There are usually two versions of higher order functions in Haskell. One is for pure functions, one is for monad-based effect for computation. One drawback of this approach is that we can at most, with the generic monads, we can at most express one effect at a time. If we want to go beyond one effect, we need to resort to monad transformers, which are very inflexible for ordinary programs. At EPFL, there was a PhD thesis to solve this problem based on dependent types. Here, we use the annotation pure F to mean that the effect of map depends on the passing function F. Actually, Lucas, he has implemented plugin for Scala, but this system is not well received in the Scala community, mainly because of the syntactical overhead, as well there is no migration story for legacy code. Now we come to capabilities. In terms of effect polymorphism, capability-based effect systems really shine here. As you can see, this piece of code are purely just standard Scala code, and there is only one change in the tab info tab signature. So we have two kind of errors. This interleaving of two kind of errors tell the tab system that the effect of map depends on the passed-in function f. So the syntactical overhead is very low. Let's see how this is possible. Before we go to the theories, let me give you an intuition of capability-based effect systems. The basic idea is that in order to produce some effects such like I/O, you will need an I/O capability. This way, by tracking capabilities in the tab system, it's possible to track effects of programs. However, there is one tricky issue. We have to ensure that the capabilities are passed as function parameters instead of being captured from the environment. Otherwise, it is possible for any functions to potentially have any effects. There is no way to impose effect constraints. For example, in this piece of code, the function pmap, it intends to say that it only accepts pure functions. But we don't have a way to do that. And then the user may pass a function f to pmap. The function f is effectful. So this is not going to work. So here we need a capability capture desampling to stipulate that capabilities can't be captured by functions. This capability capturing desampling gives us two kinds of functions. On one hand, we have free functions. They are just standard scalar functions. They can capture anything from the environment. On the other hand, we have Stoic functions. Stoic functions, they are more effect desampling. They can't capture free functions nor capabilities from the environment. Now with free functions and Stoic functions, we can solve the problem before. Here, now in the tab annotation of the function pmap, it can say that only Stoic functions, that's also pure here, can be accepted. If at the usage set, a program accidentally pass an effectful function f to pmap, there will be a typing error, because if a free function is not a subtype of a Stoic function. A little clarification of the terms. Stoic functions are not necessarily pure. They are only explicit about the effects in their tab signature. For example, in the following example, the hello is Stoic, but is not pure. Also, the function twice, if the passed-in function f have some effects, then twice is not pure. It is Stoic, but it may have some effects. Nevertheless, Stoic functions and the pure functions, they are closely related. So if a Stoic function has a type s to t, it then is pure if s is not a capability type and s is not a free function type. That's the relationship between them. With free functions and Stoic functions, it seems we get effect polymorphism for free. Here, as you can see, the map function, for it to be effect polymorphic, we need to specify that the function f is a free function type, so it can both accept free functions and Stoic functions. Then the map can be used in the context of effective computation as well as pure computation. Now we have some intuition about capability-based effect systems. Let's go to the theory. So we formalized these capabilities based on simply typed lambda calculus. As you can see, we introduced the big E here as capability type, and also the Stoic function type, the single arrow. Regarding typing rules, the most noticeable change is the typing rule for Stoic functions. As you can see, instead of using standard gamma in the typing rule, we purify the gamma by removing capabilities from the pure environment as well as free functions from the environment. However, when we set out to prove soundness of this problem, we found out that preservation is very tricky. Usually in soundness proof of simply typed lambda calculus, it depends on this substitution lemma, but this lemma doesn't hold in current system. Let's see one counterexample. It's easy to say that this lambda term, lambda z x, it has a type b to z. And the term fc, it has a type b. So according to the standard classic substitution lemma, we can do one substitution to substitute x with fc. Then we get the term lambda z fc. However, this term now can only be typed as a free function type. Preservation breaks here. What we need is a new substitution lemma to stipulate that the term used for substitution must be a value. With this change, soundness can be proved. The substitution lemma implies that capabilities only work with strict evaluation, or only pure computations can be denied. Interestingly, this contrasts us with monads. Monad-based effect systems, they don't work with strict evaluation. For example, in this piece of Haskell code, from the type signature, we can easily say the function inc is pure because there is no IO monad in the type signature. However, were Haskell to take strict evaluation, this put string will be executed first to produce some effects, and then it's dropped in this lambda. So it means a pure function can have some effects. It breaks the effect system. This causes problem because it breaks one fundamental principle of a monad-based effect system. That is, if you get your hands dirty, there should be no way to wash your hands clean. But in strict evaluation, it's possible to do that. However, the soundness doesn't guarantee that this effect system indeed works. We need some formulation of effect safety to ensure that it indeed have all the effect safety guarantees. We formulated two theorems about effect safety. The first theorem says that in a pure and inhabited environment, there is no way to create an instance of capability. The second theorem says that in a pure and inhabited environment, there is no way to call a free function. The combination of these two theorems ensures us that in a pure and inhabited environment, it's impossible to have effects. Notice that in the formulation, we emphasize the environment gamma is an inhabited environment. This is important for proof of effect safety because there might be some non-inhabited tabs, for example, from the base tab to effect tab in the environment. With such non-inhabited tabs, it's impossible to prove the effect safety. The actual formulation of the effect safety and proof is very tedious, so I omit the details here. If you are interested, you can refer to my thesis. What I'm going to talk next is about some interesting findings during the proof of effect safety. One thing that the proof of effect safety needs us to notice is about type equivalence. Here, there are two types here. They are in fact equivalent. This is because here the inner function, free function, they can't actually capture any capabilities of free functions. Otherwise, this outer function can't be tapped as a Stoic. So the two taps are equivalent. More generally, in order to prove the second theorem of effect safety, we found that we need the following axioms. The third one is the most interesting. The intuition here is that the function T1 here is effect polymorphic. So if we supply a parameter as a Stoic function, then we can type the result as a Stoic as well. These axioms, there is impossible to prove them because, for example, if T is a variable here in gamma, then we can do nothing. But there are very interesting findings. So if effect safety theorems guarantee that any functions of the type from S to T where S is not an effect type and not a free function type are actually pure. When we extended the system with polymorphism, we found some other tricky issues. That is, we need to treat type of variables as impure. That is, if X is the big X is a type of variable, we need to remove X from the pure environment. Otherwise, we have problems. For example, here, if we have a term T as this, and it's easy to see T has this polymorphic type. If we supply a capability type E to T, then we get this type, E to B to E. They are Stoic. However, after one evaluation step, we get the term lambda E Bx is basically substitution here, X with E. And this term can only be typed as this type, so preservation breaks. As I have mentioned, we're still at the very early stage of this project. We do have some open questions. For example, we look at the parallel map again. Are we sure that the execution of the P map is necessarily effect-free? In fact, no. If T is a capability type or a free function type, here is a piece of code that called the pmap function to produce some effects. Basically, what it does is to pass a list of impure functions, and then it can be used here to produce effects. So, how to impose purity of the pmap function? One tentative solution is we have in mind is to annotate the type T with pure. So the type checker will ensure we only can pass Stoic functions to instantiate T with the Stoic functions. That way, it's impossible for pmap to produce effects. Or we don't care. Just use it at your own risk, because this example doesn't harm effectivity nor soundness. And the programs, they are warned that they should pass pure function to it and use it properly. If they want to break the semantic constraint, they can do it. It's at their own risk. Another issue is about syntactical verbosity. Here we see two functions. One is to convert string to integer. The other is to read string from a file. They both have need two capabilities. If we combine the two functions, we say we need more capabilities, and also need to thread through the capabilities. As you notice, declaring and passing capabilities is very tedious, especially when there is a very long calling path or there are many effects. We can use implicits to cut down some syntactical overhead at the core set, but it doesn't save much. We can at best do as best as Java, but Java nowadays is under attack of its syntactical verbosity. So we need something better. Idea we have in mind is about to resort to capability inference. That way, I think we can cut down the syntactical overhead at the declaration set. To recap, we've seen that Stoic functions and free functions make effect polymorphism easy, and capabilities can only work with strict evaluation. We also say there are two open questions. One is to how to impose purity on the function pmap. Another is we need a better ways to avoid syntactical verbosity. Thank you.
For the inference thing, do you plan on using union types with .e and to
yes, I think maybe intersection types.
Sorry.
Yeah.
Could you clarify? I didn't get you made a comment about strictness and monads not working. Could you clarify about what you mean by that?
Okay.
It worked just fine.
So let me get back to it. It should this one, right? So what I mean here is, if Haskell to use strict evaluation, here the put string will be executed.
Yeah, that's not how Haskell works. Haskell gets a value. If you evaluate it, it doesn't print. That's why Haskell is pure.
Okay.
So you're looking how monads work in Haskell. It's quite interesting.
Okay. So maybe it's a. I look at it. Thanks. Yeah.
Hi, this is a very nice talk. So you had a value restriction, and you also had multiple value, function spaces, and both of these always make me think there might be a modal formulation of your system. Have you thought about looking at, say, some kind of comonad or something to structure to separate pure and impure code?
Sorry, I didn't get. You mean?
So you introduce a distinction between different sorts of variables.
Different sorts of variables.
The pure variables and the
You mean the type of variables?
well, for ordinary.
Yes.
You know, is this a pure thing or an impure thing?
Yeah, here.
When you have that kind of distinction on variables, it makes me think there might be a modal formulation of your system. So I was just wondering if you had looked at that.
I still didn't get your question.
Okay, I'll talk maybe afterwards.
Maybe afterwards. Okay, thanks.
Okay, and that's, thank you.
Okay, thank you.